Can anybody name the functional groups that we're using in this reaction? Starting material, to the left of the arrow, what functional group is featured there?
Ketone.
Not a ketone? Yeah.
It's an acid and a hydride.
Excellent. Acid and hydride. Joey, how'd you know that?
On my notes.
If you saw something like this on an exam, how would you know it? How could you
Red
identify it?
oxygens, pretty much. It's two.
Good.
Ketone one before the middle, and ketone, and then two.
Good. So it's the only functional group that features two carbonyl groups on either side of an oxygen. Right, that's an easy way to recognize it. Hydride, and then over the arrow, what functional group are we using? Yep.
I would say ethyl oxygen.
No, ethyl acetate. Is that molecule? What's that? Ethyl. Not ethyl hydride.
Sodium.
Most of you probably drink this every weekend. Ethanol, good. Right? So it's an alcohol functional group. Sodium ethoxide, that's just the deprotonated form of ethanol, right? So it's the basic form of ethanol. All right, so we have an anhydride and we have an alcohol. Two products that we can make from this reaction are going to result from the addition of the alcohol to either of those two functional groups, right? So one thing about this anhydride is that we would call this a mixed anhydride, meaning that the left and the right sides are different. Right, so you can see to the left of this carbonyl, there's a carbon with two methyl groups, right? And to the side of the other carbonyl, there's a carbon with two hydrogens, right? So the carbonyl that the alcohol adds to is going to determine the product that forms, the specific product that forms, right? So we'll number these carbonyls, just call them 1 and 2. Right, and these are going to be the two products that form the reaction based upon the reagents that we have in there. Right, so you can see in one product, the ethoxy group adds to carbon 1, right, and kicks out the oxygen connected to carbon 2. And in the other product, the ethoxy group adds to carbon 2, right, and the oxygen stays connected to carbon 1 as the leading group. Right, so let's take a look at the mechanism a little closely. Right, so we have our anhydride in there with both ethoxide and ethanol. Which is going to be the better nucleophile in this reaction? Yeah, the ethoxide anion, right? So again, this is just the deprotonated form of ethanol, right? So ethanol without a proton. So it seems reason that because that oxygen has 3 pairs of electrons rather than 2, right, that should be the more nucleophilic atom. All right, and so we're going to first show the addition to carbonyl 1. Right, so you add to the carbonyl, break the carbon-oxygen pi bond. Form the tetrahedral intermediate, and then this is going to undergo elimination. So electrons fall back out, reform the pi bond, right? And then we kick out the leader group. In this case, oxygen attached to the carbon. Right. And whenever you do this, one thing that you can see is that we're opening up a ring. Right? Whenever you're doing a ring opening reaction, right, or doing a ring closing reaction, it's helpful to number your atoms in the starting material so you can track where those atoms are on the product. All right, so I have a 6-membered ring, so I'm going to just number every atom in that ring. Let me start numbering the other direction. Okay, so I'm breaking the bond between atom 1 and 6. I need a 6-atom chain. Right, so I'll draw my 6-atom chain to number those atoms. Right, once I have my chain in place, right, then I can start changing things. Right, so I know atom 1 is an oxygen, so I'll change that to an oxygen. Okay, atom 2, there's going to be a carbonyl. So on atom 2, I'm going to draw a carbonyl. Atom 3, 2 hydrogens. Atom 4, 2 hydrogens, right? So I don't need to do anything on my chain. Atom 5 has 2 methyl groups. Right? And then atom 6, this is where the new ester group is going to go, right? So this is where the double bond from the oxygen formed. And also where our ethoxy group is. Put in the formal charges. Okay, gets us to the product. Questions about that? Okay. Everybody can see how we would form a different product if we added to the other carbonyl. Yeah. Okay. So this is the thing about anhydrides, right? In order to get one product from an anhydride, it needs to be a symmetrical anhydride, right? Something. Right, something like this, where the left-hand side, right, everything to the left of the oxygen looks exactly the same as everything to the right of the oxygen. Right? If everything is the same, and we add a nucleophile, then we'll make one product. Right? If things are different, right, then because we have 2 carbonyl groups, right, and essentially 2 different leaving groups, we'll say this is R1 and R2. Right? See, hopefully you can see that we have 2 different leaving groups, right? Now 2 different carbonyl groups. Okay. Questions about this? Okay. So we're going to talk a little bit about carboxylic acids today, and not necessarily ignore the derivatives, right? But in contrast to the derivatives. Okay, so these are the carboxylic acid derivatives that we've been going over: the acid chlorides, acid anhydrides, acid amides. Right? We've learned that all of these, primary reactivity of all of these is that they will be electrophilic at carbon, at the carbonyl. Right, so when we add a nucleophile, when we add a base, that nucleophile or that base is typically going to add to the carbonyl carbon, break the carbon-oxygen pi bonds, form some tetrahedral intermediate, and then if we're adding the right nucleophile, right, we're going to make a new product. We're going to undergo substitution. Right? Carboxylic acids, even though these are derived from carboxylic acids, right? And carboxylic acids, you can see structurally are very similar, right? The one key difference is that the carboxylic acid has an acidic proton, very acidic proton, right? And whereas these are going to be electrophilic, right? Meaning some nucleophile is going to add to the carbonyl. Carboxylic acids are not going to be electrophilic because their primary reactivity is to be acidic. Right, so if we throw in a nucleophile, rather than that nucleophile adding to the carbonyl, that nucleophile is just going to pluck off the proton. All right? Okay, so here's just an illustration of that property. Right. So whereas we can do substitution on the ester, on the acid chloride to make an ester, okay, we can add the nucleophile. That nucleophile adds, right, creates a tetrahedral intermediate, kicks out the chloride, and leads us to the methyl ester and then the chloride salt. Okay, if we try to submit a carboxylic acid to those same conditions, right, the nucleophile in this case is just going to act like a base because that's how this is reactive, right? And then once we pull this proton, right, hopefully you realize that we form a pair of resonance structures. And because we have electrons going through that carbonyl carbon, right, resonating through that carbonyl carbon, after we pull the proton, right, that carbonyl carbon is basically dead. It's not an electrophile at all. Because it's if you think about, carbonyl carbons are electrophilic because they want electrons from outside. Well, if we have an oxygen next door that's donating electrons into that carbonyl pi system, then it's not going to want electrons from outside, right? It's satisfied with the electrons that it's getting from itself. Right, questions about that? A really important distinction in the properties and reactivities of the derivatives versus the base carboxylic acid. So next I want to look at synthesis of carboxylic acid through hydrolysis. And we're going to really focus on synthesis of carboxylic acids from esters. Just going to draw out a really simple ethyl ester, ethyl acetate. Draw it here in the middle, actually. Okay, so here's a reaction, or two different reactions. The starting material's in the middle, and I'm just showing how these this ester will react under two different conditions. Right? Conditions to the right are acidic, right? Aqueous acidic conditions. Conditions to the left are aqueous basic conditions. 2 steps, right? We'll talk about why that's in 2 steps, right? But you can see one is basic. Right, while the other is acidic. Right, both of these were going from the ester to the acid. Right, see if you could figure out the mechanism of one of these, if not both. You guys like 5 minutes, help each other out. Right, realize that when we have acid, we typically use that acid as a catalyst, right, to make a better electrophile. Right, when we have base, right, that base is a stronger nucleophile. one more minute.
Yes, pretty sure that sulfuric acid mixes with water, you get H3O.
All right, let's go over these. So we're going to look at the acid catalyzed hydrolysis first, and then we'll look at the base promoted hydrolysis second. Right? So first of all, if you look at the reagents, right, look over at, above and below the arrow, the reagents are sulfuric acid and water. What happens when you mix sulfuric acid and water? Does anybody ever mix sulfuric acid and water in the lab? Or any acid and water?
Yeah.
Wow, that's really impressive.
Well, when you mix acid with water, it creates a volatile reaction.
Okay, have you ever felt the flask? It gets hot. Why does it get hot? Anybody knows why adding sulfuric acid to water that gets really hot?
Maybe a proton detaches from the main, and so it releases out more energy.
Say that again?
So basically, a proton detaches from the acid, and it's an exothermic reaction. That's why you get heated. So energy is coming up
Good.
because that one's breaking.
It's an exothermic reaction, right? You add a strong acid to water, you're taking the proton off the strong acid, ends up on the oxygen of the water, right? This is sulfuric acid. pK of this reaction is 10 to the 8th, right? So really far to the product side of the reaction. We learned kinetically that proton exchange, right? Acid-base reactions, not much of a barrier, right? You don't need much energy to get that proton to come off of one molecule and go on to another molecule, right? So this reaction happens really fast, right? And the heat produced in this reaction, you can feel it in the flask, right? It's absorbed by the water heats up. Okay, so as soon as you add acid to water, the first thing that happens is that proton exchange, right? So we can say that we have sulfuric acid and water in this reaction, but as soon as we mix those two things, we're just making the hydronium sulfate. All right, and so this is the acid that I'm going to use in this reaction, the hydronium ion. All right, so first thing I'll do is protonate the carbonyl oxygen. All right, what that essentially does is it takes an okay electrophile, right, and turns it into a really, really good electrophile, right, one that's really hungry for electrons. At this point, because we have a really good electrophile, we can take our water, which is, okay nucleophile, and add it to the electrophile that we just formed. Right, you'll notice I'm an acid, so I'm keeping everything protonated, right? Everything positively charged. I don't want to create any strong ions in here because they won't form under acidic conditions. Right, so this has a positive charge, right? First intermediate, positive charge, extra proton. Third intermediate, positive charge, extra proton. Right, what I need to do, this is my nucleophile, right? And this is the group that I'm trying to substitute off, the ethyl group, or the oxy group. So I need to transfer a proton from the nucleophile that I just added. reform the hydronium and then put that proton on the group that I want to be the leaving group. Right, so you can see in the starting material, this is a substitution. The ethoxy group is my leaving group. And all I'm doing, right, to get it to leave is making sure that it leaves with a proton, right, kicking it out in neutral form. So once it's protonated, we can take one of the other oxygens, use those electrons to reform our pi bond. Get to the protonated acid, and then if this is truly catalyzed, right, we use the proton in the first step, that proton's returned to us in the last step. And that gives us our product. Questions? You guys have a couple seconds to get this copy down, then we'll just go through it one more time. Okay, so again, starting with an ester, esters always have an alkoxide leaving group or an alkoxy leaving group. It's being done under acidic conditions. Right? Hopefully this mechanism looks similar to the mechanisms that we've been drawing out so far. Right, where we're protonating, right, making a better electrophile, adding some nucleophile, doing some proton exchange, and in this case, kicking out the leaving group. Right, so starting with an ester, protonate that ester first. We add our nucleophile. Right, so we're adding our nucleophile to the protonated carbonyl. We do some proton exchange, get the proton off the nucleophile, put it onto the leaving group, and then kick out the leaving group. Right, so it's not a matter of the nucleophile coming in and we kick out the leaving group right away. We have to get that proton off of the nucleophile, put it onto the leaving group so the leaving group leaves in a stable state. Questions about this? So let's look at the basic reaction. All right, in the basic reaction, right, we don't have any acid, so we can't protonate anything. Right, so the kind of the theme of the acid catalyzed reaction is that the electrophile is not good enough to begin with. Right, so we need to protonate it to create a better electrophile that our nucleophile can add to. Right, under basic conditions, it's kind of the opposite strategy. Right, what we're going to do is rather than we're going to be okay with the electrophile that we're adding, we're just going to add a more reactive nucleophile. Right, so rather than adding water, hydroxide is the protonated form of water. Right, much stronger nucleophile that can add directly to a carbonyl without activating it first. tetrahedral intermediate, right? You can see our reagents in the beginning have a negative charge. Our first intermediate is going to have a net negative charge. Right? We have to conserve that charge. Right? There's no proton that we can take off and put onto a leaving group, right? This is under basic conditions. So we're just going to reform the pi bond. Got the leaving group. Right? And we created the carboxylic acid that we want. Okay, but what's going to happen to this carboxylic acid in the reaction? Not done yet.
Is it gonna lose the proton?
Yeah, why?
Because it's under basic conditions.
Great. Right, so we form the carboxylic acid, but we have to remember that we are under basic conditions, right? We have a reaction swimming with sodium hydroxide. So whether we like it or not, right, after we form the carboxylic acid, that proton's going to be pulled right away. Right? We can't, unfortunately, we can't tell the hydroxide, all right, hydroxide, I only want you to act as a nucleophile. When the product is formed, don't deprotonate it. Right? It's going to do whatever it does. It's going to react however it needs to react. Right? So because we're under basic conditions, we're going to form the carboxylic acid, but that's going to get deprotonated right away. And then form the carboxylate. Okay, so you can see under these basic conditions, we have two steps in this reaction, right? So we're adding the first set of reagents, sodium hydroxide and water. That first set of reagents gets us to this point, right? So once we form this carboxylate, in the reaction, we're going to have the carboxylate. We're going to have our ethoxide leaving group. Right, that we lose here. We're going to have the sodium hydroxide. We're going to have the water. Right, so once we get to this point, the reaction is going to stop. Now we'll add in the second set of reagents. Right, and the purpose of that second set of reagents is to just protonate the oxygen of the carboxylic acid. All right, so mixing sulfuric acid and water is going to give us hydronium. And then that hydronium can be used to protonate carboxylic acid. Questions about this? Okay, so this base promoted hydrolysis, ester hydrolysis, also called saponification, leads to the first step, right? So it's technically saponification followed by protonation, right? So getting to here, this is called saponification. Everybody ever heard of the term saponification before? You don't have to draw this molecule out exactly. Basically, just put 3 ester groups and then some long carbon chains after those ester groups. Does anybody recognize this molecule? The general name of this molecule?
It's a phospholipid?
Phospholipid, right? We can also call it a fatty acid ester. Right? Whenever you buy olive oil, right? Most fats and oils are naturally have this general structure. Okay, if we take this fatty acid ester, triglyceride, it's also called, and treat it with sodium hydroxide and water, right? We're going to make glycerin. Right? We're also going to make this carboxylate compound. So anybody who recognizes this reaction? How many people in this room have seen the movie Fight Club? A couple of you? Okay. So in Fight Club, one of the main characters, played by Brad Pitt, Tyler Durden, I won't ruin it for you, but he makes soap in this movie. Does anybody know anybody remember how he makes soap or what he makes soap from?
The blood from the hospital or something?
Close, yeah, not the blood, but the fat from liposuction clinics. Yeah. Right? So human fat, right, takes on more or less the same form, right? The difference in fats really comes in the difference in this chain, right? Some it's a long, completely saturated chain. Others, have points of unsaturation or double bonds, right? The length of the chain is going to vary depending upon the fat. But most fats are going to take on the same structure. Right? Whenever you saponify these, right, you're creating the glycerin, but you're also creating this molecule that has the property of a surfactant. Or a soap. Right, and what makes this a surfactant or a special molecule is that one side of this molecule, there's a polar functional group, right, an ionic polar head. All right, so you get these molecules, they have a hydrophilic polar head, right? So the head of that molecule, the carboxylate group, can hydrogen bond, right? It's polar, it can interact with water, right? And then the other half of this molecule is you have this non-polar, long, greasy lipophilic tail, right? So that likes to interact with grease. Whenever you get these molecules in water, right, so if this represents the surfactant molecule, whenever you get these molecules in water, they're going to aggregate so that the polar heads are all associated with the water, right? It's going to be the low energy form. And then these long greasy tails are kind of hidden inside this ball, right, to get away from the water. Does anybody know what this is called? Yeah? Good, this is a micelle. Okay, so the way that soap works, this is a soap molecule, right? There are lots of different types of soap molecules. Again, all you need is a hydrophilic portion and a hydrophobic portion, right? when you get your hands dirty or whatever, whatever you're washing, there's going to be grease, there's going to be dirt on your hands, right? The grease is going to want to associate with the tail, with the hydrophobic tail, right? Water is going to associate with the head. So you have grease all over your hands, you're going to wash your hands. That grease is going to find its way inside of these micelles, right? And once it's in the micelle, it's not going to come out, right? Because there's water all around that micelle that grease doesn't want to interact with, right? But the soap on your hands, because it has these polar heads, right? And these little micelles are going to be attracted to water. You can put your hands under water and wash all of that soap and grease away when you're done, right? So that's, take fat, take oil, we can saponify it, create these soaps, right? Use them to wash our hands based upon the intermolecular interaction with the polar head and water and the non-polar tail and the grease and whatever we're trying to wash. Questions? Okay, we'll pick up here on Wednesday.